So we'll now talk about bubble sort. We have already discussed the idea in the class. So you start with looking at the first two elements, right? Compare them. If zeroth element is bigger than the first element, then you swap. Then you compare first element with the second element. If first is bigger, you swap, and you keep on doing this. So by the end of your first round, the largest element will reach the last position. Now, this part of your array is locked, and then you again start in the second round. Again, look at 0 and 1. So when I say second round, essentially, if you start counting the number of rounds from 0, so it's the first round. So now you again compare 0 and 1. And if zeroth element is bigger than 1, you swap. Then 1 and 2, so on and so forth. The moment your second largest element reaches here, you stop. Now this part of your array is locked, and then you again start, so on and so forth. So it's slightly different than the selection sort because we are swapping every two, we are comparing every two consecutive elements, and we are sort of bringing up the largest element to the end. So we can also do it the other way around. So just to maintain the diversity here, we bring the largest element to the end and we start locking the array from the last location. So here it's written how it goes on. So what you see here is a round zero, how the comparisons happen. And the last comparison in round zero is for the last two elements in the array. Then when you go for round one, your comparisons still start with a zero, but your last comparison is this one because your last element is locked, so on and so forth. Now, if you look at this, in every round we are comparing two consecutive elements, aj and aj plus 1. Again, like the last example of selection sort, your I here is going to represent the outer loop, which will decide the number of rounds, and J is the inner loop, which is responsible for the work done. So J is responsible for comparing and swapping. I is responsible for the range. So in round zero, right? Round zero was the time where we fix the very last element. So by the end of this round, n minus 1th position is going to be fixed. By round 1, n minus second element is going to be fixed. By round 2, n minus 3 element is going to be fixed. So this is the index of the array, right, which is going to be fixed by this round. If you talk about j, so as you can see here in round 0, you compare a0 with a1. So j is 0, j plus 1 is 1. Then j changes, j becomes 1, j plus 1 is 2. J becomes 2, j plus 1 becomes 3. If you look at j, it ranges all the way from 0 to n minus 2. Right? So the range of j is from 0 to n minus 2. Similarly, for round 1, it will be till n minus 3 because at the very end, you will be comparing element at index n minus 3 with the element at index n minus 2. Next time, it will be n minus 4. Now, can you now write the general formula in terms of I? You can look at a pattern here and follow that. So for zeroth iteration, it is still n minus 2. So can I say that for the ith iteration, it will be n minus I plus 2, right? Because if you substitute I0 here, it becomes n minus 2. If you substitute I1 here, it will become n minus 3. So it's a general formula. And which index is fixed? Can I write that as n minus I plus 1? Right? So we are just fixing the patterns here. And when do we stop? When which position becomes fixed? So very much like selection sort. You can also stop when positions have started fixing from the very end. So you can actually stop when the zeroth position is fixed. But if we work a little bit optimized way, you can actually stop when the first position is fixed because by this time the second largest element has arrived at the index 1. All the other elements are sorted, so it is guaranteed that this zeroth location will contain the smallest element. So till where do we continue? Till which position becomes fixed? We can say that till position or index 1 is fixed. That's the time we stop. We discussed this. Why does that mean the array is sorted? Because the smallest position has definitely moved to the beginning of the array. Now again, you can also make it a 0 and then work according to that, but I'm working here in a slightly more optimized way. In which round does it happen? So you can think about it logically, or you can directly plug it in the formula here and figure out. So we are stopping when the index 1 is becoming fixed. So how do I find out in which iteration, or in which round the index 1 become fixed? When n minus I plus 1 equals to 1, and you can find I from here. So I becomes equals to n minus 2. And that's the time when your index 1 element will be fixed and everything will be sorted. Now, what is going to be total number of rounds? So you are going from the value of I, or round 0, round 1, round 2, all the way up to round n minus 2. So the total number of rounds become n minus 1. This gives you the outer loop for I equals to 0. I have retained the less than or equals to sign here. So we can say that you move till I is less than or equals to n minus 2. You can also write the same condition as I is less than n minus 1. Again, one and the same thing. Okay, inner loop is a bit tricky. How do we write that? What's the range of j? So we have also computed that here. Range of j. First round 0 to n minus 2. Second round 1 to I minus 3. Sorry, n minus 3. In general, j goes from 0 to n minus I plus 2. Or n minus I minus 2. That's all. Now you can fix up, write everything in this code. So we have a bubble sort function being called here. The definition is here. We already have computed the range of I goes from 0 to less than n minus 1. So 0 to n minus 1. Range of j is again 0 to n minus I minus 1, but since n minus I minus 2, but since there is a less than, I'm going to write n minus I minus 1. And if array of j is greater than array of j plus 1, you are going to swap both of them. Now, if you look here, the swap function here has a different signature than what we used in selection sort. So I'm just showing you different ways to swap here. So here we are passing the array itself, so that any change that you made to this array in the swap function will be reflected on the original array. And I'm passing the two indices. These tell me the locations which I want to swap. So when you call this swap function over here, the array comes as it is here. Whatever change you make to this variable a is reflected in the original array. This value of j is copied to this value of I. So basically, if you were swapping locations 2 and 3 and you call this function, I will be 2 and j will be 3. And all you have to do is, in this particular array, swap the element at index 2 with the element at index 3. And you can again use the same temporary variable code here. So you can declare a temporary variable which is initially a of I. Right, this time I'm not using I, I'm using a of I, because I is not the value that I want to swap. I is the index of the element array that I want to swap. So now t holds the value of ai, and now I can modify ai to hold the value at aj, and then I can modify a of j to hold the value of the temporary variable. So swap function is complete, and hence the code for bubble sort. Let's quickly look at the time complexity. So it's given to us that in the inner loop, what we are doing for each value of j, we are definitely doing one comparison. And if the value is true, we are doing one swap. So again, both of these operations take a constant time c. All we have to count is for how many number of times this gets done. And again, let's actually start from round 0 and not round 1, because I think our rounds here are starting with a 0, right? Okay, so round 0, j goes from 0 to n minus 2, which means it runs roughly n minus 1 times. Not roughly, actually, exactly. So for round 0, it runs n minus 1 times. For round 1, it runs n minus 2 times. For round 2, it runs n minus 3 times, so on and so forth. Our last round was round number n minus 2. That's right. Last round is n minus 2th round. And for this round, how many times will it run? So for round 3, it will run n minus 4 times. So for this particular round, so if you fix, you can see a general pattern over here, right? For round 0, it is n minus 0 minus 1. For round 1, it is n minus 1 minus 1. For round 2, it is n minus 2 minus 1. So for this particular round, it's going to be n minus 2 minus 1 this many times. So you calculate it, n and n will get cancelled over here, and you will get a constant value here, which is 1. Right? And there was no, we could have also logically thought about here, since it's the last round, what happens in the last round? All the positions are fixed, just apart from position 0 and position 1. So you are fixing position 1 here, which will take you just one comparison. So that's all. So if you want to do a total here, it becomes n minus 1 plus n minus 2 plus n minus 3 plus n minus 4 up to you get a 2 and up to you get a 1. Right? And so total time becomes, each of these takes constant time, but you repeat this constant time these many number of times. So see into this whole things come here. So on and so forth. Now, this is a very general AP formula where you have 1 plus 2 plus 3 up to n minus 1. So you can directly use the AP formula here. So it can be n by 2 to a plus n minus 1 into d, which is roughly n into n minus 1 by 2. Right, and which becomes order of n square. In general, also, you can directly see here that if you ignore all the constants here, you are roughly doing n plus n plus n plus n times, which is order of n square. The complexity of this code becomes order n square. So please remember that when we are doing this analysis right now, we are talking about the worst possible case. We are assuming that every swap happens. We are assuming that every exchange happens. So the condition for that will be when your array is sorted in a descending order. Let's say something like 7, 6, 5, 4, something like this. So you compare 7 with 6 and a swap will happen. 7 with 5 and a swap will happen. 7 with 4 and a swap will happen. So whenever we do analysis of any sorting algorithm, the worst case is it doesn't depend on the value of n. N is always going to be very large. Worst case is how your array is. And in this case, worst case is when your array is in the descending order.